Hi, and welcome to Dr. V's Chemistry Webcast. Today, the focus is acids and bases, a little bit about their properties, and a lot of attention to the theories of acids and bases. So what I wanted to do, I apologize, I'm working outside today because it's just too nice to be outside, so there are a lot of birds in the neighborhood, and they're being very, very chirpy. Just ignore them. They're fine. I wanted to go back and talk about operational definitions. What are some properties that we can test to determine if a substance is an acid or a base or neutral? All right. We talked about this a little bit, but I wanted to revisit it before I went on. So acids we associate with pHs that are less than 7. We do know that acids will react with active metals like magnesium and zinc to release hydrogen gas. So that can be a test for the presence of an acid. They have a sour taste. Think about the taste of lemon and citrus fruits, all right, that sour taste. And they'll turn blue litmus paper red. So these are all different tests we can do to determine if an acid is present. We have a similar set for bases. We associate pHs greater than 7 with basic solutions, all right. In the presence of a base, the indicator phenolphthalein will turn pink. Red litmus paper will turn blue. Bases have a bitter taste. If you've ever gotten soap in your mouth accidentally, that taste is, we say that it's bitter. And a lot of medicines have a bitter taste because sometimes the compounds used to prepare them are basic in nature, and then we have to put flavorings in to hide that flavor. And they may have a slippery feel. So if you think about if you've washed your hands with a bar of soap, how your hands feel, or if you've been washing windows with an ammonia solution, and you've gotten it on your hands, that slippery feel we do often associate with bases. Now, tasting things is not a safe way to recognize whether something's an acid or a base. You certainly don't do that in a lab situation. And if you're taking a test on acids and bases and your teacher asks for ways to determine, if something is an acid or a base, you're not going to talk about tasting them. But we do know that these associations exist. All right. But we knew about acids and bases and could classify substances long before we had a theory. The first theory wasn't proposed until 1887 by the Swedish chemist Svante Arrhenius, who won the Nobel Prize for this work in 1903. Where this came from is that Arrhenius had been very interested in the behavior of substances in solution when they dissociated to form ions, and that's really his dissertation work was on that. He continued it. And there's some good stories here, but we're going to go on and just talk about the theory. So according to Arrhenius, he said, well, what makes an acid is that acids release hydrogen ions when they're dissolved in water. All right, so Arrhenius' theory is really all about being dissolved in water. That is actually part of his theory. But the key component is that acids release H+ ions. All right. Examples of Arrhenius acids are things that we often think about as acids. Nitric acid. Hydrochloric acid. Notice they both have H+ as the cation, right? We call these monoprotic acids because there's one hydrogen ion. We can have diprotic acids like sulfuric acid. Notice there are 2 hydrogen ions, right? We can even have triprotic acids like phosphoric acid, which is often used as an ingredient in sodas, right? It's got 3 hydrogen ions to make a neutral formula, so we can have different classifications of our acids. Okay. Arrhenius also had a theory for bases. He said bases are substances that release or generate hydrogen ions when they're dissolved in water. So again, we're in aqueous solution, and you have to have hydroxide ions to be a base in this theory, right? So our examples of Arrhenius bases include sodium hydroxide, potassium hydroxide, magnesium hydroxide. Notice they all have hydroxide as the anion in the formula, right? So this was the very first theory of acids and bases. It was groundbreaking, right? There hadn't been one before. Certainly seems Nobel Prize worthy, but there were some issues with the theory as well. No theory is ever perfect, right? But there were some things that it was hard to explain, all right? I do want to point out with Arrhenius theory, notice that these are all ionic compounds. The anion is hydroxide. And I do also want to point out a common misconception. Alcohols, right, which are organic compounds, and they have hydroxyl groups, OH groups, but it's all covalently bonded. They are not Arrhenius bases, all right? So be very careful. Make sure it's an ionic compound if you're asked to classify substances. So I was talking about the issues with the Arrhenius theory, and one of them is the substance ammonia, all right, which we often use as a cleaning solution, all right? And you may have some in your house. All right, it's got the formula NH3. All right, here's the Lewis structure. And we know that ammonia neutralizes acid, which is a hallmark of bases, right? Acids react with bases to form water and salt. It turns litmus paper blue, right? So wait a minute, that sounds like a base to me. But Arrhenius theory says that bases make hydroxide ions. I don't see a hydroxide ion here, all right? And Arrhenius did try very hard to come up with a way to include ammonia in his definition, but it didn't really quite work. But it clearly behaves as a base. It is a base. So how do we explain it? Well, Arrhenius theory really doesn't. And it wasn't until another acid-base theory was proposed a number of years later that we were really able to explain this behavior of ammonia as a base. All right, so this brings us to Bronsted-Lowry theory, which was proposed in 1923 by Johannes Bronsted, who was a Danish chemist, and Thomas Lowry, who was an English chemist. And they both came up with this idea independently of each other and both published it, and they both get credit. So it's a fairly different theory from Arrhenius theory. The acid definition is actually not that different from what Arrhenius said. And so this means anything that's an acid in Arrhenius theory is also an acid in Bronsted-Lowry theory. Right? Arrhenius theory is largely of historical importance, and of the acid-based theories, Bronsted-Lowry theory is definitely the most important one, the one that's emphasized the most. All right. What really made this theory important was that they expanded the definition of bases. So now that we have a way to explain ammonia as a base. So let's go on and talk about that. All right. In Bronsted-Lowry theory, acids are defined as substances that are hydrogen ion donors or proton donors. A hydrogen ion, H+, is basically a proton. And so we can say it's a proton donor. Bases in this theory accept hydrogen ions. They take the hydrogen ions and we call them proton acceptors. All right, so here's a little graphic. All right, acids give H+ ions away. The bases take them. In Bronsted-Lowry theory, you can't have something acting as an acid without something else acting in the capacity of a base. All right, so the acids are hydrogen ion donors. All right, now we had talked about acetic acid as an example of an Arrhenius acid, and acetic acid, which is shown here as the Lewis structure, is also a Bronsted-Lowry acid. But I do want to point out that just because hydrogens are in a compound doesn't mean it's automatically an acid. There are 3 hydrogens shown in green, and they are not acidic hydrogens. So those 3 hydrogens attached to the carbon atom in the Lewis structure are not acidic hydrogens. They don't get given away. They stay with the molecule. The hydrogen atom in red that's attached to the O in the carboxylic acid group, that's the acidic hydrogen in acetic acid, which is a monoprotic acid. That's the only hydrogen that can be given away. So we often write this as HC2H3O2 to show that it's a monoprotic acid. So Bronsted-Lowry acids give hydrogen ions away to bases. So if we have hydrochloric acid, oh, that's an acid. What a surprise. It's going to give away its H+ to a base, which in this case has to be water. So I'm using this kind of curvy arrow to show that. When that happens, all right, so water is going to act as the base because it's accepting the H+, all right, I'm going to make 2 products. The HCl is giving away an H+, all right, which is going to the H2O. So the H2O, it takes its H+ and makes H3O+, and HCl gave away its H+, and I'm left with Cl-, the chloride ion. So H3O+ is kind of important, all right, we call it the hydronium ion. And the reality is in water, you don't really find just protons floating around, all right? You don't find just isolated hydrogen ions. They really form complexes with water. To even write H3O+ is really something of an oversimplification, all right? This would show one H+ complexing with one water molecule. It's got a trigonal pyramidal geometry. It's got an overall charge of +1. It's probably more than one water molecule complex, but that gets too complicated. So we always write H3O+. And you'll often find that we can write H+ or H3O+ interchangeably. We certainly are trying to communicate the same thing, that it's acting as an acid. And depending on the situation, you might write H+ or you might write H3O+. You do need to make sure that, if you're writing an equation, that it's still showing conservation of mass. But this leads us to the idea of conjugate acid-base pairs. All right, when an acid gives away its H+, what's left is its conjugate base. All right, and we can't just have an acid without a base, and so we have to think about what the products are and labeling that. All right. So our conjugate pairs are what's left when an acid gives away an H+, or what you form when your base accepts that H+. And those conjugate pairs differ only by a proton in their formula. We're going to spend a lot of time talking about that. All right. So let's say we have nitrous acid, HNO2. I hope you recognize that that's an acid, right? It's got H+ as a cation. So that's our acid. And it's, say, going to react with ammonia, which we just talked about can be a base in Bronsted-Lowry theory. All right, so when HNO2 gives away its H+ to NH3, all right, I'm going to be left with nitrate ion, right? So HNO2, the acid in the forward reaction, when it gives away H+, makes NO2-, and then NH3 is going to make NH4+ when it accepted that. All right, so HNO2 was the acid in the forward reaction, NH3 was the base in the forward reaction. We can actually think about this as a reversible process, because it is, although I didn't write a double-headed arrow. So the nitrate ion in the reverse reaction has a capacity, has an ability to accept an H+. And so we call that the conjugate base. We use conjugate for the, you could think about it as the products, or you could think about it for the reverse reaction. All right, so NO2- is the conjugate base, and ammonium ion is the conjugate acid. All right, so when HNO2 gives away H+, it makes NO2-, and that's a conjugate pair. Notice they only differ by H+ in their formula. When NH3, the base in the forward reaction, accepts the H+, it makes NH4+, which is its conjugate acid. NH3 and NH4+ are a conjugate pair. All right, and this is something that gets emphasized a lot in terms of Bronsted-Lowry theory, identifying these conjugate pairs. It's really about writing the reactants and products for the equation when the H+ gets transferred. So I found this graphic that sort of summarizes it all, and I thought it was a really nice, clear explanation. All right, it does have a double-headed arrow indicating that these are reversible processes. All right, so the Bronsted-Lowry acid, HA, can give away an H+ to the base. When the acid gives away its H+ ion, it's left with its conjugate base, which here is represented as A-. When the base in the forward reaction accepts the H+, it forms its conjugate acid, Hb+. So we have two conjugate pairs in any equation, right? In any acid-base reaction of this type. Ha and A-, whatever those formulas are a conjugate pair. B and Hb+ would be a conjugate pair. So this is something we'll be practicing. So to find the conjugate base from an acid formula, you have to remove one H+ from the formula, one and only one H+. And you do have to pay attention to charges when you're doing this. So let's go and do some examples. If my acid is HCl and it gives away its H+ because it's acting as an acid, the conjugate base that I form is chloride ion, Cl-, right? Because the H+ got removed. If my acid is HBr, the conjugate base is Br-. Notice I take away H+, I have to have a negative charge for the conjugate base so that the overall charge is conserved. If my acid is HNO3 and I give away an H+, I'm left with the nitrate ion, NO3-. And if I have acetic acid, HC2H3O2, notice it's a monoprotic acid, only one hydrogen is ionizable. I'm left with the acetate ion, C2H3O2-. So I've got four conjugate pairs here. Let's practice going in the other direction. If I have a base formula and I want to find its conjugate acid, I have to add one H+ to it. Again, I have to pay attention to the charges when I do it. So if my base is NH3, which we know can be a Bronsted-Lowry base, the conjugate acid would be NH4+. If my base is hydroxide ion and I add H+ to it, I get water, which is neutral. If my base is water and I add H+ to it, I get the hydronium ion, H3O+. And if my base is carbonate ion, CO3 2-, and I add an H+ to it, I get hydrogen carbonate ion. Notice the charge went up by 1. All right. So one of the things I want to point out here is that I've got water as a base, as in one example, and I've got water as a conjugate acid in another example. This brings me to a very important term, all right, which I'll mention in another slide. Not quite yet. First, I want to do a little more practice with conjugate pairs, all right? So you need to be able to look at the formula and decide, is one an acid or is one a base? Do they differ by only one H+ in their formula? So if I look at carbonic acid, H2CO3, and the carbonate ion. Is that a conjugate pair? Well, they both have carbons and oxygens, okay, but there are 2 hydrogens in carbonic acid and no hydrogens in carbonate ion. That's not a conjugate pair. They don't differ by 1 H+, they differ by 2 H+, so they don't meet the definition. If I have hydroiodic acid and iodide ion, is that a conjugate pair? Yes, it is. They differ only by 1 H+. If I have HOBr and hydroxide ion, are they a conjugate pair? Nope. There's no Br on the right side of the slash, and also they don't differ by just 1 H+. They're not a conjugate pair. One's an acid, one's a base, but they're not a conjugate acid-base pair. If I have phosphoric acid and dihydrogen phosphate, is that a conjugate pair? Yes, they differ only by 1 H+. If I have water and hydronium ion, is that a conjugate pair? Yes, that differs only by 1 H+ in their formulas. If I have hydronium ion and hydroxide ion, is that a conjugate pair? No, it doesn't meet the definitions. Yes, hydronium ion can give away an H+. Yes, hydroxide ion can accept an H+. But they don't differ by 1 H+ in their formula, so they don't meet the definition. What about acetic acid and acetate ion? Is that a conjugate pair? Yes, it is. They differ only by 1 H+ in their formula. Okay, so I had mentioned about water, how it had been an acid in one example and a base in another. This is actually a really important term. There are substances that are amphiprotic, meaning they can act as an acid in some situations, and they can act as a base in some situations, and it really depends on what else they're interacting with. What's the other species? All right. We say that they're amphiprotic. Sometimes you'll hear amphiteric, but amphiprotic is more correlated with Bronsted-Lowry theory, which is our emphasis. All right. Water is a very important example of this. Water can undergo what we call autoionization, where it can act as an acid and give away an H+ to another water molecule, which can act as a base by accepting the H+. And when we do that, it establishes an equilibrium where hydronium ion and hydroxide ions are formed. Now, this particular equilibrium really favors reactants. In pure water, although this reaction does happen, a vast majority of the water molecules are still H2O, and you only get tiny, tiny amounts of hydronium ion and hydroxide ions. The equilibrium constant is really, really tiny. And that might come up again later in the unit. But right now, I just wanted to mention this idea that water can act as both an acid and a base, and can do it with itself. So, which of the following species are amphiprotic? Give away an H+, can accept an H+. Can water do that? Yes. If you know only one example of an amphiprotic substance, no water. Okay. What about hydrogen carbonate? Can it give away an H+ and act as an acid? Absolutely. It would form carbonate ion. Can it accept a hydrogen ion? Yes, it can do that and form carbonic acid. So that is an amphiprotic species. What about sulfate ion? Well, I'm looking at the formula, and yeah, it could form hydrogen sulfate ion, but it doesn't have a hydrogen ion to give away. So that is not an amphiprotic species. What about nitric acid? Okay, it can give away an H+. It's an acid, right? HNO3. But to accept another H+ would give us a very strange formula. That's not going to happen. So HNO3 is not amphiprotic. What about hydrogen phosphate? Does it have an H+ to give away? Yes, it does. Does it have can it accept an H+? Sure, we could have H2PO4-. So that is an amphiprotic species. What about sulfuric acid, H2SO4? It has H+ ions to give away, but I don't see how it can accept an H+ and without giving us, that just isn't going to happen. That's not amphiprotic. So one of the things I wanted to point out is that your hydrogen-containing polyatomic ions, so hydrogen carbonate, hydrogen sulfate, those guys tend to be amphiprotic. So these are the two most important acid-base theories. Arrhenius theory, just as a recap, right? Our acids release hydrogen ions, bases release hydroxide ions. Historically, this was the first theory, and it's very useful. But it's more of historical significance than anything else. Bronsted-Lowry theory encompasses it. Anything that's an Arrhenius acid is still going to be a Bronsted-Lowry acid. And anything that's an Arrhenius base is still going to be a Bronsted-Lowry base. But the opposite is not true. You can have things that are Bronsted-Lowry bases that are not recognized as Arrhenius bases. Right? So in Bronsted-Lowry theory, our acids are proton donors, which is very similar to what Arrhenius said. But our bases are now proton acceptors. So we've really broadened the definition of a base, and so we can explain ammonia and things like that. Okay, now there is actually a third acid-base theory, and it was proposed by Gilbert Lewis, who was a Massachusetts native and spent some of his career as a chemistry professor at MIT. And you might remember him from Lewis structures, which we spent a lot of time learning how to draw. All right, and his acid-base theory, which was also proposed in 1923, is an extension of his work and his emphasis on electron pairs. This is an enrichment topic, but I'm going to mention it because it's really interesting, and when you go on and take more chemistry in the future, this will be very important. So according to Lewis theory, which is the broadest of the theories, all right, Lewis bases are electron pair donors. So if you draw a Lewis structure and there's a lone pair on an atom, maybe a central atom, doesn't have to be a central atom, that's a potential Lewis base. And Lewis acids are species that can accept an electron pair. All right, and so this really broadens the theory quite a bit, all right, compared to Bronsted-Lowry theory. So a classic example of a Lewis acid-base theory is ammonia, which we recognize as a Bronsted-Lowry base. But you see it's got that lone pair on the nitrogen, right? And it can give that away. And in fact, it's going to give it away to the boron, which is not got a full octet and could, in theory, accept another electron pair. All right, so it's going to be the Lewis acid. And when they react together, they form a covalent bond between them, all right, where the bond involves the two electrons that came from that lone pair of nitrogen. So we call that a coordinate covalent bond because both electrons in the bond came from one atom. So we do get a covalent bond between them. This really broadens our definition, particularly of acids. Thinking of acid-base reactions where we're not limited to aqueous solutions. We weren't with Bronsted-Lowry theory either. But we're also not limited to things that are H+ ions for acids. It really opens that up. So that really makes for some very interesting chemistry. Right? So I'd like to wrap it up. Arrhenius theory talked about acids generating hydrogen ions, bases generating hydroxide ions. Bronsted-Lowry theory talks about acids being proton donors, bases are proton acceptors. We have our conjugate pairs. We have amphiprotic species that can act as either acids or bases. And then we do have this more broad theory of Lewis theory where acids are electron pair acceptors and bases are electron pair donors. I think we'll stop here, and I hope you have a wonderful, wonderful day.